about is mainly from my master's thesis work, and then a lot of it is going to PhD research. So throughout all of these years, Jurgita Kaputidė-Dzikienė has been my supervisor, and she helped me with her insight, natural language processing world. Are we okay? Okay, so I want to first present some general ideas, and I'll quickly go and grab my cheat sheets. Okay. So really, the main sort of field in which a lot of this is done is organic chemistry, or at least it's based on. Sorry. Thank you. So I think we can all remember some organic chemistry from our high school years. So there's really two basic concepts. Essentially, that organic chemistry is something that is fundamental to all life and biochemistry that fuels pretty much the entire Earth and life on Earth. And there's really two ways to notate or write essentially what happens. So on the top here, you have the graphical way of drawing out what's happening. And then on the bottom, you essentially have a more of a concise symbolic notation. And really, what happens is you usually have smaller blocks that form more complex molecules that usually have some sort of functions. And so that's all interesting, but when it comes to real applications, and when you have to do these reactions, I have to build blocks within laboratories, you're faced with the reality that it's not as simple, and that if you have to accomplish something, you need an instruction on how to do it. And so with every reaction comes an instruction on how to do it. And it's generally, it has a framework in which you can work. So you usually add up the reactants, you heat it up, you mix it, then it usually has to cool down, and then you do some operations to get the target product of what you're looking for. So it might form crystals, and then you have to collect the crystals, so you have to filter out, and so on. So that's kind of the framework that you're working with. And so here are just a couple of illustrations on what I mean when I talk about more complex actions. It's not just about adding something together. It's so, for example, here on the top, you have crystallization. So essentially, you can pour some water, for example, into the mixture, and then you have some crystals forming. On the bottom, there's distillation, which is a fairly simple concept, and I think everyone knows about it. But these are the sort of apparatus actions that we do in the laboratories. So if we think about this sort of task of saying, okay, if we have a bunch of these reactions and a bunch of these instructions, can we come up with some sort of artificial intelligence, algorithms, methods to predict essentially these procedures for any compound? And there's going to be a point at which you have enough data and you're going to be able to do it. So this is a sort of a more of a fun example, but it's a good way to think about it. It's work in the laboratory is a lot like work in the kitchen. Essentially, you have to perform some actions to achieve some sort of result. And these actions are rather quantized. So you have, for example, some sort of actions like let's boil something, let's fry something, or we have to cut something up. And then these actions have parameters. So these parameters can be temperature or duration, or if you're chopping something up, it could be the size of the resulting blocks and so on. So if we think about this example, there are quite a bit of algorithms that developed especially for this type of generation, for instruction generations for food preparation. But these are quite simple, and you can even come up with a couple of regressors for parameters, and that's going to be enough. But if you're preparing something really complicated, you're going to have multiple ingredients that you're going to have to either supply the algorithm as an input. So that's not easy. You're going to have different states, and there's ambiguity in the states of the ingredients. So, for example, you have, for example, spices. They might not be even mentioned, or the spice itself, the token or the word, can mean quite a bit of different spices. For example, you can have olives that taste different. Then you can have various types of milk and so on. And then you have you might have some sort of implied ingredients that are not even mentioned in the procedures or in your data set that will occur. And if you don't supply it, or you don't care about it, it's not going to predict as accurately. So this essentially also could be salt, like salt and all sorts of spices. And then the resulting procedure is going to be long and complicated with multiple steps. So how do you deal with that? There's not really any good answer. Most of the way that it's done essentially is you come up with sort of a sequence generator, like a sequence or so on. But that's difficult because you essentially have parameters of continuous parameters, for example, temperature. So if you essentially tokenize that, like a temperature from 0 to 100, then you have 100 tokens, and that doesn't make sense. And so how do you deal with all of that? So the reason this issue comes up of generating procedures is that essentially, if you need to accomplish a successful synthesis, you first of all have to have a reaction product. What do you want to do? And so this could range from various active molecules, so essentially the entirety of pharmaceutical ingredients, also agrochemicals, all sorts of plastics, coatings, and so on. Then you have to have a synthesis plan. Essentially, you can come up with ways to synthesize the same molecule in many ways, right? So what are the building blocks that you're going to use? Because in some cases, they're readily available that you can purchase, and sometimes not. And then finally, you need procedure of the synthesis. And that's really the task here. So there are multiple initiatives for AI research in this area of generating molecules, sort of active compounds, new molecules. There's really kind of two ways of doing it. This is essentially either you have the generative model, sort of illustrated here on the top. You have a known inhibitor, like it could be pretty much any molecule that has some sort of pharmaceutical effect, and then you can generate from that multiple molecules. The second way is essentially you have some sort of target. So here is a protein, and then you have some sort of active site, and based on that, you can create sort of various methods for creating new molecules that's going to fit in there, and will have an effect on the protein, not just automatically as it was done with a lot of computing power, but now with AI. There's also interesting research done by here by IBM in Zurich. So essentially, you can come up with really good ways to select the starting ingredients, and all of this is AI powered. But you don't really have that sort of procedure generation algorithm, and there's not a lot of research done. And the reason it's interesting and relevant is because you have a huge cost associated with developing new drugs, essentially. So here's sort of an illustration that you start with a lot of substances, and as the years go by, so it can be up to 12 years and more in some cases, and obviously billions of dollars. to really finish up with a single product that enters the market, and there's an incredible risk associated with it for the company that develops these drugs. So if you want to accelerate that, you really want to focus on the first half of it and essentially come up with even more molecules to test. And the faster you can do it, the more, essentially the cost will be much lower for the final product. So there are some advancements, not just in AI, but essentially in the acceleration of how these molecules are tested. So that's one of those is essentially robotization of a lot of the processes, and one of those is high throughput screening. So here's just a GIF to illustrate that. Essentially, you can take a lot of molecules and test them if they're effective rather quickly. There's not a lot of variance associated with it. There's also a lot of money and time, and researchers working on how to develop new drugs and come up with the new drugs and new molecules. And we've seen that, over the years, billions of dollars of investment into these companies are accumulating. So we're going to see a lot of results, but really the final sort of piece in there is really automated synthesis. And there are some interesting developments, but it's nowhere near as completed as the other steps. Because it's a lot more complicated, there are a lot more different steps and different routes you can take. So here's on the right, there's a helper robot. Essentially, it has to navigate the entire laboratory. There's a plan sort of illustrating that complexity, that you have a lot of equipment that you have to work through. So it's difficult. And essentially, the entire idea that all the way through just sequencing of folding proteins, through target identification into even clinical trial monitoring and post-registration monitoring. We would like to, as AI scientists, that it would be AI-powered, and a lot of these things would work in also sort of closely, would be monitored by multiple AI processes, and that would lead to high throughput of new drugs being identified, developed, and so on. And so we would like to see it not in 11 years, but maybe in a year, and so on. So first, I'll come back to that, but I'll start with the data that's available. Essentially, I've been working with pretty much the only data set that's freely available. It's about 3.7 million of reactions with their procedures or instructions of how these syntheses are done. And it's a structured data set. So it has an XML file structure. But what you can see, so here in the green, we highlight different steps that occur. And essentially, the data comes from just raw text and descriptions for humans to read. So here's the full sentence, essentially, of what's been structured here on the top. So it says, okay, so we add something that we stir for some amount of time. Then in red, we have parameters. So in one case, that's a continuous parameter of duration, so 2 hours. And then we have a solvent label, essentially xylene or something. So we have like raw segments of the text data being fragmented, and then some information is extracted from them. And so we can use this data to try and come up with sort of AI methods to solve this task. And so here's one of the solutions that we came up, and this has been in the works, and this is something that we've been testing. So essentially, it starts with user input of what molecules they use. Essentially, they have to supply the reactants and the products. So this is in a graphical sort of format because chemists like that. And then there's a SMAS notation, essentially a symbolic line representing the same structures. And so we first start with action sequence there on the right, and then we come up with an AI algorithm to predict the action sequence. And then for each action, we come up with algorithms to predict what is going to be the, for example, temperature of each step, or if there's going to be some sort of, some of the steps, for example, have a type. What are you going to partition? And then, for example, if you're going to dry, what do you use for the drying process? So essentially, you have to predict labels. And there are also two unique sort of tasks, so I won't talk about them much, but essentially, the idea is where do you put the reactants in? Because it's not necessarily at the beginning. So for example, in this case, you put the first and the third reactant in, and they correspond to the input. And then you also have solvents that additionally get put into the entire system on the reaction flask, not necessarily at the beginning. So there's quite a bit of variation. So here we have all the different tasks. So and generally, task relates to each step. So there are some steps that don't require any parameter prediction. Then there's a bunch of them that have temperature and duration. There are some that have just temperature. So that's essentially a regression task. For classification of types, so it's a traditional classification task for 3 steps. And then you have multi-label classification where there could be multiple classes for, again, a bunch of steps. And there are, as I mentioned, like these 3 unique tasks. One is, first of all, you have to predict the sequence, and then all the reactant and solvent addition. So when we worked on these tasks, first is you have to vectorize the data somehow. You have to represent the molecules to the neural networks in some way. So we first did with learned embedding. Essentially, it's the idea that we treat each symbol as, for example, you would treat a word in a sentence. So that didn't work too well. I mean, it was a starting point. Then there were 2 interesting methods, which is essentially molecular fingerprints. So it's an established algorithm in which you can just calculate sort of a binary vector of a molecule, and then you have, for example, 6 molecules participating in a reaction. You can concatenate those. And so here is the illustration of the fingerprint. So the black essentially is just zeros, and then the white squares are ones. And one of the things you can first, of course, notice is that it's a quite sparse matrix. So it can be difficult for neural networks to understand this. And the idea that then we came up with, essentially you can use an encoder. So you ask the neural network to take this input that's on the left and essentially reproduce it with a bottleneck layer in the middle there. So interestingly, LSTM works quite well. And then you can essentially just take the 2 top layers, and that works as an encoder. And you can stick that on some other neural network. You essentially lock the weights of the 2 layers, and then you can do some sort of prediction tasks. And so here is the picture in the middle, and that's the compressed vector, or essentially something that comes out of the LSTM layer. Again, so these are just sort of here formatted visually. They're not just like these square ones, but for visual representation, it's okay. And so the middle picture is rather small, and I've tried to size it accordingly to the first one, essentially comparing the size of it, and then you have essentially values ranging from 1 to 0, depending on the activation function, but you could be -1 to 1, but essentially you have all these numbers in between. And the idea is that, well, you know, these big autoencoders that have lots of weights can hopefully pick up on the meaningful parts of this fingerprint and compress it into a much smaller one, much denser one, and then come up with something much better. And interestingly, that works quite well. Okay, so I first want to mention when I was doing my master's thesis, pretty much at the end of it, so IBM here also are working on, so it's research group in Zurich. They're very it's a very large group. There's at least 3 PhD in computation, so very smart people, and they've been working essentially on this task, the same data set. Again, interestingly, they use the same symbolic notation. Again, for the same task that they're solving essentially the same task, and then they're using the same sort of idea of predicting just a step, or like step names, essentially, what you're going to do. And then essentially in the tokens that I'm coding, well, which of the reactants I'm going to put in here, noted in the dollar signs, and so on. So interesting. So they opted for a single neural network that's going to just predict everything as a sequence. It's a transformer-based model. It works quite well for the task that's being solved. But essentially, the results are that you have about 3.6 accuracy for the entire action sequence. So that's a very low. Like if we saw that, that's definitely not the best algorithm, or we would say that that's definitely not a good algorithm, but that's the best that they could come up with. And then essentially for one-step synthesis, so essentially like those easiest examples, then you have about 72% accuracy. So it's interesting, but there have been some choices made. They've opted out of some steps that are not necessarily, that should have been there, and they've excluded some of the essential steps. And also, when you use this essentially design of the system in how you predict all of this procedure, you come up to the problem essentially of continuous variables, and then you have to use ranges, and then you have to encode them into some sort of tokens. And the ranges of the, for example, values are well, in this case, extremely large for field such as chemistry that requires precision. So like this range in the plus sign, that's not that important. For example, -50 to -10, that's a huge amount of, that's a huge range, which is, you have to think about, well, why do you do that? And that doesn't really come up, doesn't result in a good solution. Okay, so our solution is a little bit different. And essentially the way we predict the sequence is just we predict the next step based on the previous ones. So 2 inputs, essentially the first input being the same, what are the reactants and the products, and then the second input essentially are the steps before the step we're trying to predict. So it's a fairly simple scheme. And what adds more complexity is that, for example, if you want to predict what's going to be the temperature of some step, for example. So the problem is that steps can repeat, and essentially then you have to come up with 3 inputs. So number 1 being what are the molecules of the reaction. Number 2, what is the action sequence. So here in 2. So you can do some sort of one-hot encoding or whatever works. And then number 3, you have to essentially give a vector of which step are you trying to predict, because the essentially 2 inputs, for example, for heat step, because it's in 2 positions, and so there can be much, there could be essentially a lot of variation in between different steps. So prediction for continuous variables, here are just the results. So I don't give too much importance on the accuracies and the results and so on, because we're looking to see, well, can this task be solved? Can we get some sort of realistic understanding on what do actually we need to come up with good solution to this task? And really the design of the system is much more important, but nevertheless, the results are rather good. So this is R squared. Essentially, the heat duration is quite difficult, but the rest of them are still above like 0.9, I think. Then you have essentially a couple of steps that need to be that you have to predict what is the type. So for example, a good example is the recover action. So you can recover that which you filter or that which filters. So essentially, if you filter something, then all the solution that goes through the filter, it could be the case that you have to collect a liquid, or that you could collect something that sits on the filter. So that's essentially a type, and you just have to classify the step. Again, fairly good accuracy. When it comes to label classification, it's a bit more complicated because each step essentially asks what solvents you're going to use. So you might have 2 or 3 solvents, so that makes the task much more difficult. And the problem with a lot of these steps is essentially that you have to collect quite a bit of data, and the data extraction from the data set again is difficult because for each step you have to come up with a bunch of labels, essentially solvents that you're going to use. And because everything is extracted from raw data or like raw text data that is written by scientists and over a long period of time, so the data spans from I think like 3 decades of research, of organic chemistry research. So names have changed quite a bit. Or let's say the trivial names of the solvents. There could be errors. The way it's written is different. So for each of the steps, you have to write quite a large code that sort of entangles the heuristics on, okay, well, which of the solvents it's written in this simple paragraph. So there are difficulties, especially with solvent names like ether and diethyl ether. So it's quite difficult. And then the unique task. So essentially the important one is the sequence prediction. How well can we do this? So at this point, we've done quite a bit of tests, and it's actually, I think, a little bit better. The reactant and solvent addition is fairly low as far as accuracy goes, but it's a complicated task. And luckily, it's not as important because when do you add reactants? You can predict that, but it's not as important for the chemist. You know, a lot of times they're going to know what sort of are they doing. So that's not the most important part. So that's not too difficult. So here's one of the examples of the illustration for like neural networks that we use. So again, you can see 3 inputs. We've come up to the realization that, well, these encoders work really well. So that sits, I think, on the 2nd input. And then the most optimal neural network types are generally some sort of mix between feed-forward and LSTMs. If you use LSTMs, in some of the cases and some of the steps do have quite a lacking data. You know, you have about 20, 30, 40,000 data points. So then you can see that, well, actually feed-forward works better than LSTMs. But if you have more data, then you can actually push the system and you can get better results with LSTMs. So, okay, so one of the advantages of the design is that you can just take the single step and you can come up with standalone tools for predicting what are going to be the parameters in one of the steps. So we've done that, and we've analyzed one of the steps, which is the purification step. Essentially, it's a 2 neural network system that allows scientists to predict the solvent system and ratio. We published the research and methodology in a fairly good journal of organic chemistry and molecules. And we're currently preparing methodology for the crystallization step. So I want to show you the examples because I think that's the interesting part. So on the left, you have a concise version of what would a real instruction would look like. So quite a bit of steps, quite a bit of stuff going on. And on the right, you essentially have the predicted version when the entire system is trained, optimized, and running. So in this case, we have almost an identical prediction compared to the original one. And you actually even get some of the interesting information, additional information that's not written into the entire paragraph of the original instruction. So, for example, on the second step, the stir. So, as humans, we don't write that we stir at room temperature. We just say we stir, and then the default is, well, that's room temperature. Because we predict everything for the entire instruction on the right, we get temperature of 24. So there is some difference, but it's interesting that we do get additional information. So there are some examples, for example, year, which is not a perfect prediction. For example, the action sequences are almost the same, but some of the parameters differ. So it's difficult to say, well, is this better or is this worse? And that's the difficult bit when testing these systems, that essentially you have to test everything in the lab. For example, do you dry with magnesium sulfate or phosphorus oxide? And it's difficult to know because some of these are completely interchangeable. And then there are some examples where the predictions are bad. So I want to show you some of the interesting things that you can do when you come up with a different design, or like what the design allows you to do. So traditionally, we just, when we predict a sequence, we give the first token, which is the start sequence token, and then it predicts everything else here on the left. But we can see that, for example, in the first step, there are two reactants, the R1 and R2, being added at the same time. And we know that, for example, one of those has to be first dissolved in the solvent, and then the second one is added later. So we can just give the system instantly two tokens of the action steps, and that the system would predict what's left. And interestingly, the system understands, or the neural networks have this intuition on what happens, and you can see that it puts correctly that the R1 gets dissolved in DCM, and then the R2 essentially slides down and is being added in the second step, and all the rest of the steps don't change any of the parameters. I mean, there's minimal difference in like 5 minutes on the stir temperature, but that's irrelevant. Essentially, all the parameters remain the same. Or you can add some of the steps. For example, if you know that here after the fourth step here on the right, you want to add extraction, like one of the actions that you want to do. Or for example, if the neural or the system got it wrong and you want to correct it, you can add multiple steps, and you can say, okay, predict everything after the extraction. And interestingly, it still does predict fairly correctly the remaining sequence. Even more interestingly, for example, if you change the step here, which is the extraction, with here on the right precipitation, what we would expect is that here in the extraction we use a liquid, and then that liquid has to be also washed and dried. If you use precipitate, from what you've seen, those little crystals forming in the flask, what you immediately would think about is that, well, you have to filter, because I already have my target molecule in the crystal form. So I'm going to just filter off the excess solvent or something, and I'm going to have my final product. And so you can see that with this yellow line, immediately the next step that the system predicts is filter. And then the rest of the steps are going to be just washing and drying that move down. So there is an intuitive understanding of what the system understands, that some of the actions have consequences and the rest of the steps have to be different. And so here's another example, essentially the same. If you say that, no, I'm not gonna do the washing or drying, I want to do purification. It predicts in green all the parameters that you're gonna use, and the steps here, those two steps of washing and drying, are not needed anymore. And essentially it ends with yield, which is just the final step of saying like, okay, you got it, that's the end. So I want to finish off with just some outline of future work. So first is dataset expansion, and there are some methods for data augmentation. But the dataset expansion is not an easy step. First of all, because you have to analyze raw data. There's a lot of grammar analysis just to fragment the paragraph. You also have to draw from multiple databases to come up with good mapping for the molecules. And then you also have to do all of the steps that have been done in this work to come up with a fairly good and clean data set. Also, the use of transformer neural networks that have been testing out, and it seems like these are fairly good, and they do take a little more time to train, but I think a lot of the tasks, essentially neural networks can be rewritten and trained again. We can improve the molecular encoders, so we can come up with more ways to represent the molecules. Essentially, we can add multiple types of molecular encoding, so we can show the neural networks all types of molecular features, not just the fingerprints. An interesting way of looking at this is also that the parameter prediction for all the steps have to be based on previous steps, or not just on previous steps, but also on the previous parameters, which is not included in the system currently. And it's quite difficult to do because you have to train like very specifically all the steps. And also, we got to come up with a user-friendly interface. I mean, that's a trivial task, but I think it still allows for people to test and see how the system works. So thank you very much.
So thank you, Mantas. We have Q&A session after other two speakers. So right now I want to introduce you Gediminas. Are you here? Yeah.
Hello, everyone. Good evening, everyone. Well, very good presentation from Mantas. I believe my presentation would be like a sales pitch, but forever, I will continue on that. So my name is Gediminas. I'm representing company Agmis, and I would like to give you a different size of this artificial intelligence and machine learning, what we are facing everyday life in the business perspective. And before jumping into that, in the manufacturing industry, I would like to a bit introduce where we are coming from. So basically, Agmis company started as a software development company, but through our 14 years in the industry, we are always looking for new ways how to assist the customer. And this led us to like position ourselves in the different branches. And Agmis stayed on the customer software development to support customers on their business needs. And the Blue Lark department was founded to also bring best worldwide experiences for such a huge enterprise as Salesforce. And we are the first one certified in the Baltics and to bring the value for the customers in these countries. And EasyFlow department, why it was brought into the market, because as I mentioned, we are looking for innovations that customers would be needed from the business side in the future. And we want to be the first ones who will bring them and influence and help them to improve it. And for today, where we are operating in the different industries, it's like the retail industry. So we are helping customers in the physical stores to help from the entering the store from the first steps into collecting the goods, and also to handle the queues at the checkout zones, and also to prevent the losses in the self-checkout machines while customers are trying to fraud and to steal at them. And I will be talking mostly about the manufacturing industry and a slight touch of the unmanned aerial vehicles industry, just to show where the artificial intelligence and machine learning is leading to. So a bit numbers, just to understand what the manufacturing industry is facing. So the biggest economy engine, US, yes, United States. And according to the latest KPMG company survey, up to 2030, there will be like 2 million positions unfilled, and the manufacturers will face a huge impact on that. And this will cost them like $1 trillion to the whole US economy. Of course, it's not the only problem on that, because like what we are living now for, I know, 2 years, yes, the COVID is striking us and changing all the conditions and isolations and etc. So it's very sensitive for the manufacturing industry, because if few employees are found in the shift that they are like COVID positive, the whole shift must be isolated for 10 days at least, and then they have somehow to change it. So they are more struggling on that. And of course, like social problems like diversity, gender, and maybe like, I don't know, also like problems for the generations, like that they are willing to find better, like more, I don't know, better career than to say, let's go into manufacturing, which was like the position for 20 or 30 years ago. Yes. And what manufacturing companies are looking and what they're doing, how to solve this problem. So according to the McKinsey company survey, like 60% and even more, depending on the region or the continent, manufacturing companies are using artificial intelligence and machine learning technologies right now. And they're going that deep and deep and deep and using, because they are facing huge problem for the shortage of the people. And they're using like for most common uses in that industrial cases, like quality assessment to check if their production is manufactured in a quality way, and how to lower the cost for the manufacturing, and of course how to put a bigger margin, and other like categories like inventory management, how to forecast the demand from the market and how to supply it like on the lowest amounts, and how not to freeze your money in the warehouses and give away what to manufacture. And we made a survey or like a market research and entering the industry, trying to solve the problems and partnering with them, trying to understand from their business perspective to convert it into the code that all the processes would be manufactured in most efficient way. And we started from very, like I would say, simple tasks, with the computer vision. We started to work with the construction industry, because we saw that this industry is like most less digitalized, and we try to use the video streams that they are having on their sites to say whether they are performing for the construction processes in the timeline or in the roadmap, where is the most common working areas, and what the employees or like construction workers are doing in there, and how they are performing. And this led us to in like manufacturing industry, like okay, I see that the presentation is not that which I'm showing, but okay. So this led us to manufacturing industry and human safety insurance, because as we're talking with the manufacturers a lot, they say that we cannot like watch the whole video streams all the day, because it would be too expensive for us. And we suggested them, okay, let's use computer vision and have a virtual assistant who is never tired. He can monitor 24 hours per day, 7 days per week, yes, 365 hours per year. And also to bring value to see whether your employees are strict to the requirements, because it costs a lot for the manufacturing companies, and also to show the real situation where they must improve that. And not all the cases are each time take out of the shelf product. So our mission is to help customers also like to improve their operations by customizing it according to their business needs. And this acquires, of course, more development, more data to be acquired, and models to be precisely working. And on these cases, we're assisting the customers like to solve the problems basically on the custom projects. And as various projects are coming for us, the complexity or the tasks might be as hard according to the business. For example, this case was we need to create an architecture like for the system to work on edge, because there was no possibility to run everything in cloud. Because vessels are far in the sea, they are drilling the mines and collecting the oil, and there were cases like to monitor the separate areas, because there are vessels coming to supply these platforms, and according to the human safety, there no people must be in the exact places, because it's for the safety issues. And we were also checking if the employees are wearing the exact protective gear. And the newest partnership, as I mentioned, we are looking for new partnerships, new ideas, and how to create the products together with the different industries. So now we are partnering with a German-based company.
Your work can feel much smoother.
Sorry for that.
Monday.com Work OS. This smooth.
Okay, skip that. And we are partnering with a robotic company which manufactures robots by itself and also reselling big brand robots. So what they are doing, they are influencing, educating the industrial customers how to solve that employee shortage, because, for example, in Germany, the labor cost is huge, and the demand for those professionals, it's also very big. And we are working with them, assisting from not hardware, but from the technology side, like creating skills, like to detect the Gauss measurement rates, or like to use like a skill, the PPE detection, personal protection equipment detection, and from that to collect the data to represent it for the customer where they need to improve their operations. So also another interesting case, the complexity to show that, for example, one food manufacturing company come to us asking how we can help us to solve the problem when we have a standalone workers working in the shifts, and there was a case that one of the employee lost his conscience for 4 hours, and he was noticed only after that, and they didn't want to recreate that scenario in the future. So they asked what we can do. Okay, let's use the devices like smartwatches and etc. But they said, no, it's not possible. According to the rules that we have in production line, if it will fall, it will cause us a lot of damage. So we were eliminated not to use any wearable hardware. So we suggested to use video analytics that to watch the human pose estimation, and in real-time notification, we can send an alarm if employee has fallen, slipped, and etc. And talking about the quality inspection, so we see that there is a big demand, how to change the human labor for that, because the process takes too much time. The labor cost is very, very expensive. So the task was how to detect wrinkles and defects on the manufactured car seats, and to send these results for the robotic hand, to use steam to eliminate it. And our developers created the flow, the process, and the whole architecture, how to detect those wrinkles and send those coordinates to the robotic hand that it would be eliminated. And the goal for us was set okay, in the pilot we must achieve 40 seconds, and in production we need to be not more than 3 seconds. So our results were quite impressive, and manufacturer was quite impressive, and he wants to scale up to using another manufacturing sites. And as I mentioned, I will touch a bit of the UAV sector and managed area vehicle sector. So in this, what we're doing, we are partnering with the UAV manufacturing companies and drone operators. So they're basically doing the flights, collecting the data from the different sources, like using RGB, photogrammetric data, and also LiDAR. And merging these two sources, we are able to provide insightful data for the power line supplier, and detecting using, of course, machine learning, computer vision technologies to collect the data from these captured images, and also to show that in the reports. And for the LiDAR data, we need to detect like overgrown plants to show them on the map where they must like to go directly to eliminate all those overgrown bushes or trees that are hitting directly into the wires. And of course, this data also shows how to improve and to manage their labor that they have, and also to minimize the cost for these maintenance tasks. So on that, we are assisting the business working together, like technological side and understanding like customer needs. So thank you very much. I hope you like what you see. Sorry for some videos with some bumps. And if you have any questions, we can talk about that later.
Yeah, thank you very much, Gediminas. Yeah, and we have presents also for you and for Mantas. So this one, and there's like name. Yeah. This for you.
Thank you very much.
Okay, so we have last speaker, Jev from Vinted and board member of Artificial Intelligence Association of Lithuania. So
let's do a quick show of hands. I have two slides, two sets of slides. So don't open any of them just yet.
yeah.
The reason is that Linus reached out to me end of last week and asked me if I could do a presentation, and I was not sure if I should prepare something new or should I do something old, relatively old. So there are two options for you. Either you could watch me present an experimental set of slides that I've put together over last night, or you could watch an older stack of slides that I presented just a few weeks ago at Lithuanian Young Mathematicians meeting. All right, thanks a lot. So, hi everybody, I'm Jeff. I'll be talking today about, I will be giving a talk today on the very experimental deck of slides about the idea that I've been thinking about for quite some time. And I thought I'll use this quick opportunity to prepare, which forces me to prepare some slides and put some of these ideas
into some structural form. Yeah, and this is the long title of the talk. This is from the book by Steven Strogatz. He is one of the most cited mathematicians in the world, and he's kind of working on popularizing science. And he has this book, The Joy of X. But anyway, we'll get to that. First, I'll introduce a bit myself. Interesting setup here. So I've did a master's in applied mathematics, published a paper there where we worked on detecting exoplanets using machine learning, specifically Gaussian process. We detected 50 exoplanets and published in a Royal Astronomical Society. And I did a PhD, published at CVPR, and also created a dataset for nuclei segmentation, and that is currently in the process of being acquired by a big pharma company. And I've also worked on climate data for quite a bit as a senior statistical scientist at Servest. There we worked on all sorts of things from climate modeling to remote sensing. And this is kind of an example of, it's a PDF, so no example. Essentially what you would have seen here is exoplanets flying and how we detect them, but we can skip that. Another thing that we worked on is, I've worked on is climate modeling. I'm not sure how many of the people here are familiar with how climate modeling works, but most of the political decisions today regarding climate change are informed by models just like this, where the whole world is split into a large grid of cubes, and within every cube we have a set of differential equations, partial differential equations that are solved forward in time and backwards in time to fit them, and then we model the climate 100 years forward and see how that climate changes. But the cool thing is that you can imagine that whole process as a video, a sequence series, and then you can try to apply neural networks and predict how that evolves. And that what you do with that way is that you save computational time, because you don't no longer have to have massive computational scale in terms of GPUs. You can instead have a neural network that models all of the cube for you. So that's kind of about my background. Today I worked at Vinted. Here's a Vinted data science analytics team, and this is me over there. And today, before that, I was working as a lead of a machine learning team, and now I work as a staff decision scientist where I work on experimentation and causal inference. So for today's talk, because it's experimental talk, I want you to think conceptually, use analogies together with me, and ask questions and discuss. So let's start. All of you hopefully can load the QR code. Make a sign in voice. The code is Batman that you've already loaded. So you have to say Batman once you've loaded it. Batman. Excellent, thank you. We got one up. Yep. Okay. More Batmans? That was just like 5 Batmans out of what, 20 people? Okay, so you should see the first question there. Can you see it?
Yeah.
What is it?
What data science is all about to the beginning.
Yep. So now you have to answer that question. Someone already gave an answer, Batman. Just a few words. So far we have answers: Batman, formulation, random forests, noob, data, AI, Excel sheets, make computer do stuff, loads of unstructured data, again Excel sheets, math doctor. Okay. Has anyone ever? I suppose that people have already finished typing, or if you're still typing, I will continue. So the talk that I'm going to talk about today is about conspiracy stuff and seeing patterns within all levels of hierarchy, and specifically in the data science community. Hopefully by the end of this talk, you will put me somewhere with the stuff that I'm talking about, you will put me somewhere on the spectrum of either a complete conspiracy or something that makes a bit of sense. That's the feedback that I want to gather from you today. And this will also provide me how I should develop this idea further. By the way, this is not so much of a joke. There is a nice publication from end of last year from MIT where they engaged themselves in a Facebook group of anti-vaxxers and monitored what they discussed, and they did some nice analysis on this. And I really recommend reading that paper. You actually will realize that anti-vaxxers and scientists think very much the same way. So that's just an anecdote. Highly recommend checking out that citations will be always here at the bottom. So getting to the Kaggle conspiracy, what is it about? So think about what a Kaggle, everyone knows what a Kaggle is, by the way. No? Okay, so what Kaggle is essentially a website. You go to that website, there are a bunch of data sets there. There are metrics that evaluate how good you are performing on the data set, and everyone competes to get as high possible result on that metric. And that's all what it comes down to. So random forests, neural networks, people are throwing them at the data sets and trying to get as high as possible result. Is it clear? Okay, cool, excellent. So the Kaggle conspiracy. The usual Kaggle competition looks like this. So you have some data set of size n. You have test data set of some size on the right. You have most of the data sets on Kaggle are assumed to be IID. So what that means is independent and identically distributed. The environment is static, which means stationary. There is no underlying change. And you have an offline metric provided for you. And that's how all Kaggle datasets look like. And the conspiracy I have is that the popularity of Kaggle tremendously influences how data science evolves. What do I mean by that? So that leads us to the next question. It's, by the way, the same slide. I'm just gonna run the next poll. So can you see the new question? Can someone read out it? Volunteer? No? Okay, so the next question is, what was the last data science analytics or machine learning problem you were working on, or working currently? What was your offline metric, and what did you try to impact in your business sense? Question. You perhaps could use an example of some of the presentations that we just heard where people worked on some problems if you look inspiration. Asset integrity, MSE, okay. So while people typing, I'll leave the poll going. So remember, I said that the Kaggle really forces us to think that all of the data science problems that we face, or machine learning problems, or whatever we want to call them, face the exactly same structure. The IID in a static environment, and there is offline metric and dataset provided for you. And if we look at most of the popular textbooks published within machine learning community or data science community and promoted within data science community, they all follow the same structure. So if we pick this book here, who recognizes this book? Yeah. So this is a book by Abhishek Thakur. He is one of the Kaggle grandmasters, very famous, very cool, has a lot of Twitter followers. That's how we measure how significant you are in the machine learning community. We measure it by Twitter followers. So he had published this book approaching almost any machine learning problem. And the book content goes pretty much like this. It's about setting up your computer environment, supervised versus unsupervised learning, doing cross-validation, evaluating metrics. By the way, in this case, he means offline metrics like mean-squared error, accuracy, F1 score, whatever. Arranging machine learning projects, feature engineering, feature selection, and hyperparameter optimization. And this is what seems to be the main conversation within the whole community. It's good, by the way, that he talks about reproducible code. This is very important. That's kudos for that. But is that really the case with the whole data science? And I will argue that because we focus so much on the learning algorithm and on the optimization of the offline metric, by learning algorithm, I mean, for example, neural networks and stochastic gradient descent, because we focus, this is also not gonna work. This sucks. Hold on. Can you see the visualization? Probably not. So you see here that we are not really convergent to the global optimum. What we have is that we bump up our efforts as a community, we increase that learning rate, and in the end, we don't converge to the optimum of where we would like to be as a community in terms of learning data science as a whole. And by the way, there's a very nice article that I cite here by Zachary Lipton. He's a professor at Carnegie Mellon University, and before that he worked at Amazon, where he writes about the deception of supervised learning. And because through Kaggle and through popularization of Kaggle and the people related to Kaggle, supervised learning is becoming really popular, but it's really not the only essence of what comes down to real data science. The real data science problem looks something like that. So this is an example from Microsoft advertisement system. It's from the paper by Leon Botu, a quite famous statistician, mathematician, whatever you want to call him, on counterfactual reasoning and learning systems, the example of computational advertising. So this is the actual causal graph of their advertising system. And we're trying to intervene on the model scores, which produces the scores of how successful will be an ad or an ad given the query. So we have a query from the user, we put it into scores algorithm, which also takes ads from the database of ads, and then it evaluates which ads will likely score, will produce the highest click-through rate given the current query of a user. And when the data scientists or machine learning engineers work on that problem at Microsoft Bing, they don't have to just think about offline metric, they also have to think about the online metric, the business bottom line that they're trying to impact. So this could be a click-through rate for them. How likely are people to click on the ads and generate revenue? But they also have to work, not just probably about one online metric, but work on, so we can work in hierarchies. They probably have to think about multiple business metrics like user retention, how likely they are to retain a user if they show them too many ads. They probably have to think about other metrics as well, like successful search, that they should get successful search in the end and not just ads. And that also has to correlate with a longer term metric of how likely your user is to continue to use your service. So you can imagine that the model that you're constructing has all of these down the line consequences, and it's not just about you optimizing accuracy or you optimizing F1 score. It's all really about the bottom line that you are trying to affect. And we as a community don't talk sufficiently about that. And perhaps we should look a bit into the mirror. And by the way, don't take this talk too seriously. It's really an experimental one. I told you, noticed you. Because we often criticize the education that we get at university when we look at, for example, statistical education that we get. But everyone might remember when you get statistics 101 and you learn t-test. And you learn t-test and you think, where the hell am I going to use it? Why am I learning it? It looks so boring. And then you learn about t-test, you learn about all sorts of other tests, about correlation, and all kinds of other tests, and you have no idea how to apply them actually in practice, and that's really the case. Scientists don't know themselves how to use them because we have crisis in psychology, for example, in terms of reproducibility. So no, we really don't know what are the assumptions behind these tests, why we should use them, and when we should use them. But actually, we're not that different. If you go to scikit-learn, it has exactly the same graph for which algorithm to use when, for supervised learning. And I really want to sink that in, that actually we should probably be thinking way deeper about data science and machine learning and what we propagate as a community. Because this doesn't really make good problem solvers. It doesn't really teach people how to think about online metric. It doesn't teach really about multiple objective optimization that we have to do in practice when we solve practical problems. What utilities do these problem solutions bring to the stakeholders that we are working with? And this really comes down to this quote from David Hand, a statistician from the UK, on this constructing statistical questions. There's too much current statistical work, and here by statistical I mean data science or machine learning, takes a superficial view of client's research question. Because what we often do is that we see supervised learning problems everywhere now because of the narrative that we have in the community. And we use these models, specifically here, because of solid history that they have, and most importantly, because of the available software, without considering in depth whether the questions that we are trying to answer, in fact, those which should be asked. And this is really important. Are we trying to answer the right question? Because the word science in the combination of data science is really about asking the right questions. So I highly recommend reading the articles by David J. Hand. He has another really good article called, what's it called? Something about fallacy of supervised learning. Really nice. So what I would argue is that instead of being algorithm-centered and really getting too excited about algorithms, the learning algorithms that we have, we should be goal or problem-centered and use Lego-like approach to problem solving. And to do that, we could probably draw some inspiration from mathematics, specifically from the map of mathematics. So, by the way, check out this article on Quanta magazine. They made really nice visualization of mathematics and how different fields of mathematics connect to one another and what problems they allow to solve. So we can try to construct a similar map of data science. And this is kind of where the experiment comes in, is can we construct a map of data science and that way show the holistically what the data science is about instead of it being just about supervised learning and Kaggle. So at the basis, if we think of it as a Lego blocks and what are the basic building blocks of data science, these are probably probability distributions. And there is a very nice YouTube video by a channel called Mutual Information. This is a data scientist from Lyft, where he shows very nice visualization using MANIM how different probability distributions relate to one another. So at the basis, we have different probability distributions, and this is their relationship. It's notoriously hard to understand what's going on there, but whatever, let's ignore that for a bit. So we have probability distributions. Then we have graphical models. Graphical models allow us to represent what a data generating process we're thinking about. Then we have representation space within which we observe our data. So you've heard a talk before about computer vision. Computer vision operates on grids, specifically on pixels. Pixel is just a grid of data points. Then we can have more complicated data sets on groups. I've talked about climate data. It's a sphere, so you can represent it as a group. Then you also heard the first talk about molecular design. This will be graphs. And then you can have more kind of complicated representation spaces. And of course, you have tabular data. Now we put them aside. Now we have time series or irregular time series. And these can have underlying statistical processes from the probability distributions that we talked about. So they can be a stationary time series, the green one. It can be non-stationary time series like type-dependent mean, where mean changes over time, or variance changes over the times, or covariance changes over time. And we can keep populating that whole map of data science, and we'll see that the supervised learning is only a little part of it that touches only so many things, and not really as many things as Abhishek Thakur says, that it touches almost any machine learning problems that you see in practice. So you'll see that Bayesian modeling there, causal graphical models are there, potential outcomes are there, which becomes really handy when you have a pandemic, because you need to know what a treatment effect is of a particular intervention that you do. You need decision theory to actually define the online metric that you're thinking about with your stakeholders. You need adaptive experimentation, for example, again, if you have two potential interventions, say a very expensive treatment and a very expensive acquisition of agents to whom you can apply intervention, then you need to use adaptive sampling to figure out and determine the treatment over time. And then you've got to have optimization and sampling to optimize the models of your choice. And in the end, you have reinforcement learning. So this is me trying to build the map of data science. Now the question to you will be, let's see. The question to you will be, what is missing in the map of data science? Essentially, you see here Bayesian modeling, potential outcomes, adaptive experimentation, reinforcement learning, causal graphical models, probability distribution, all sorts of stuff. What do you think is missing from that map?
From this picture.
Yeah, from this picture. If we were to build a complete representation of data science, what would be missing from it? Problem formulation, excellent. Connections, unsupervised learning, experiment tracking, problem formulation, domain. Okay, very good. Keep coming. The reason I didn't draw connections here, because I wanted us to then think of how we could use this map of data science in education. So instead of education being about learning what is the latest algorithm that we should learn now, transformers, or we should learn ResNets now, or we should learn something, I don't know, support vector machines. Instead, we could look at the set of tools that we have to formulate problems holistically and think about, okay, what problem do we want to imagine now? Let's say we have take this bunch of probability distributions, we put them on a grid, and we have them, their parameters vary non-stationary dependent on time. Suddenly we have a complicated problem that we need to think about, and then how can we reverse engineer this problem? And if those of you who read Andrew Gelman, he's quite a famous statistician, contributor to Stan and a whole bunch of other things. He actually, in his classroom, he gives this exercise, and a few other statisticians do that too, where they divide the groups of students on two sides into two groups. And one group has to design a statistical process, just dream up a statistical process using the tools like that. And the other team has to reverse engineer the statistical process. And that really forces you to decompose the problem that you're trying to solve. But the core that I'm trying to argue is that when we start to think that way and we look at the whole map, perhaps we can broaden and just make it more accessible to all of the people to see the whole picture and apply this to their problems. That's really it. Thank you.
Okay, thank you, Jeff. Maybe we have some questions from Victoria. Yeah, Linus.
So, Jeff, so you're saying that the 15 billion parameters neural network is not the way to go for us to learn and try it?
Well, it's just one of the tools. It's just one of the tools, essentially. It's not the complete picture of everything that we need to know to solve problems in practice.
Yeah, David?
So, Evgeny, you are experienced data scientist, right?
Perhaps.
So, how many of these do you know?
How many of these do I know?
How many of these are you an expert
In none. I don't think it's important to be an expert. There is an interesting study. If you read, you know already that book because I told you about it. It's a book called Range. And in that book, they talk about the research by Tetlock something. He was at Berkeley at that time. And he was working with intelligence services from the United States, where they ran a competition from 2012 up to 2016, to 2012 up to 2016 on different teams competing with intelligence services within the United States who can make the best predictions about certain political events. And what they found is that the teams that performed best had very diverse experience. And they had very diverse experience and they had a broad knowledge of things. So it's really that range when you know a whole bunch of different things that benefits you in real life. And they also had another example there of where they analyzed the most successful patent registering people, essentially the inventors, which inventors succeed the most. And within different organizations, the people who produce the most successful and the largest amount of successful patent applications are people who have not just a specific scientific field experience, but actually who have worked in different scientific fields overall. And then they start to see connections, how different modeling approaches, how different problem representations connect and allow you to solve different problems. And if we had that complete representation of data science, then suddenly we would start to see analogies between different data science problems that we worked on in the past. So you don't really need to be an expert. You just need to know, oh, this problem looks like, I don't know, non-stationary time series prediction on a graph or whatnot. And then you kind of know where to look for, who perhaps worked on that problem and what did they do in that problem. If that was a long answer.
I have one more question from YouTube watcher. So how to increase the human trust in AI?
How to increase the human trust in AI? I don't know if I'm qualified to answer this question. So I perhaps someone in the audience knows.
I think since you're a human, you are qualified.
You need to educate them.
Perhaps that would fit. Yeah, thank you. That's it, I guess.
Yeah.
All right, cool, awesome, thank you.
Thank you. This is a gift for you.
Oh,
This is
nice.
incredible. presentation. Yeah, so thank you everyone who's watching us on YouTube and who's today here in the auditorium. So, and right now we have networking session here in this place. Oh, and Davide, our president from AI Association, want to also say a couple of words about association. Yeah.
I will be very brief.
Okay.
So this is the mic, right?
Yeah. So amazing to be in Kaunas for the first time, doing this AI Lithuania's AI Association meetup. So nice. So many times people from Kaunas have come to Vilnius to attend live events. I'm so happy that we finally came back to Kaunas and do this first meetup. What's even better, I guess, is that in 2 weeks we have one more meetup, also in Kaunas, and this time, since we have like a few universities in Kaunas, is going to be in Kaunas Technical University. So see you in KTU in 2 weeks. Not sure how to pronounce it in English. Kaunas Technical University in 2 weeks. So amazing free speakers, so many good discussion points which I can't wait to talk with all of you about. So many people which I have been waiting to meet in person. So thank you all for being here. Have a great evening. Looking forward to talking with you, and bye-bye. Yeah, thank you, Davidas. And yeah, I think that's it for today. And we have networking session right now and snacks and drinks for everyone who's there or who's watching us on YouTube Live. Have a good evening. Bye.